Hello and welcome, dear viewer, to another video. Today I thought I'd hack on spcasm, which is my little assembler thingy for SPC 700. Read this in the description, I don't know. It assembles this weird architecture that was basically only ever used in a single relevant chip, and that relevant chip is the audio coprocessor of the Super Nintendo. So yeah, that's why the architecture is interesting. Anyways, if you follow me on any social media, probably know that I've been working on this a lot recently. And what I want to do today is implement some of the stuff that's in my main to-do list. I've been doing a bunch of stuff that's not on here, but I thought I'd actually do some of these features because they're rather useful. So I thought I'd actually do incbin or include or both today, which are very important macros. I'll do incbin first because it's a lot simpler. I already know that. So incbin, as you might be able to see in the WASM old style syntax module manual, it doesn't really show here, but this is the old style syntax module of WASM, which is a well-known compiler for a bunch of old architectures. Its incbin command just includes the binary contents of some file into the object code, the binary at that position. It's like kind of a standard macro that you will find in a bunch of assemblers. Azar also has it. Oops, I'm scrolling too fast. Incbin. They use a slightly different syntax for the range. WASM always uses this comma syntax in all the in all their macros. As you might be able to see if I scroll through some of those, like this, for example. I'm not entirely sure which syntax I should follow. So to be clear, WASM can't compile SPC 700. If I go into general, let's see if that loads. Where's the different... Okay, nope. Let's actually look in here. Yeah, okay. I mean, you can see it here. The different assemblers that are supported. Most of them are like rather common ones. Even the 8086, probably the 16-bit one originally, but it's mostly older architectures that are supported by WASM. And Azar, in turn, is actually also an SPC 700 compiler. If I go to the very top, it's a multi-architecture SNES assembler. Like, it's also very much intended for patching existing ROMs and not just writing new ROMs, but it can do all the architectures you will need on the SNES, including the SPC 700, but it doesn't have any specific features for the SPC 700 apart from just, supporting all the opcodes, which I guess is the bare minimum. It also has this very nice inline architecture, which I want to support at some point, and you can switch between the architectures within a file, which is rather interesting, but my assembler just supports SPC 700. But of course, I would like it to be kind of compatible with Azar. That would be kind of nice. Let's go back to wherever that label is, incbin down here. I don't know what syntax we'll use back here, but let's just actually start with including a whole binary file, which is, how we start. So let's not actually Alt-Tab to OBS. And I'm very confused why my computer is doing crazy shit. So how are we gonna do this? First of all, incbin, the symbol, is not yet recognized by my lexer or my parser. It will just be treated as a label, and that label will actually then probably break everything because of the quotes behind it. So yeah, if we actually want to have it be recognized, we need to add it to the macro symbols list. Now, the great thing is that I've written my own macro, which can automatically parse all the enum constants I put in here. So I can just incbin here, and it will be able to parse it from this exact name. Now, that's the first step. This will already enable the lexer to recognize the symbol and put a special macro token, macro keyword token, so to speak, into the token stream. Now, of course, we need to handle it in like all the places here. So luckily there's only one. We need to be able to print it out. I haven't put this into the macro yet, but also in like here, I don't actually want to put this display into the macro, into the like into the Rust macro, not into the spcasm macro. Yeah, because there's some different things here. Sometimes I want to, for example, byte and word are just aliases, so I don't actually want to print byte and word here. That's why I'm only doing this parsing, quote unquote parsing thing here, with the generator proc macro, procedural macro. Yeah, anyways, implementation details of the assembler aside, that should give us the macro. Now the next step is to have the grammar recognize it. For that, we need to go into the grammar. Now, this might seem kind of strange. This is a file that looks a bit like Rust, but it's actually not. It's actually a specialized domain-specific language for the LRLR-pop package, which is a class of parser, which is basically LR1 parsers, I think, that is generated. So Rust code is generated from this file. And there is some Rust code in here for like determining what happens when we see certain tokens and certain elements of the syntax tree. And like all the code that I'm giving it here is basically just constructing the syntax tree. But there's also some things like this, for example, which doesn't fit on a line. Let's close this. This, for example, which is actually just a syntax definition. It says that a line is a line, so that's just the name of a non-terminal, is the non-terminal label for instruction, followed by any number of new lines, and that might or might not exist, and that is the label. And then we have the instruction or macro, which is another non-terminal, and then we have more than 0 new lines. This might be kind of familiar if you know how grammars are usually notated. It has some limitations, especially because of ambiguity, because it's LR1 and not like a generic context-free grammar. I have some other documentation about how I actually need to adapt the real text source code, lex source code, into a format that this parser can understand. However, I don't think we should have any trouble putting things in here. Here's the macro non-terminal, which contains all the macros directly or indirectly. This list has already gotten rather long. However, I don't see a reason to change it because most of those macros are rather simple. So I think I'll just add it down here. Now, the macro symbol that we're going to use, the incbin, is not recognized by the parser yet. The LRLR1 parser can provide its own lexer, but you can also make it use another lexer. And if you use your own lexer, you have to do this extern enum token thing and these two type definitions, and that basically tells tells the parser what symbols to map to what internal symbols and whatnot. It's all very well documented on their documentation. So we need to put the specific token that we are using internally and give it a string name. That string name can be anything, but of course I'm gonna give it the name incbin. And that is, let's look into token. That is in fact a kind of token. You see the token enum here. It's kind of weird because it's things that are not, like, they are sometimes higher level than what you would typically call a token. For example, the where is it? Yeah, for example, the register token is like a generic token for all kinds of register keywords. And if you look down here, we actually take the single register token and split it up into 7 different tokens, depending on which actual register we're talking about. So in fact, we're not introducing a new token, we're just introducing a new sort of sub token under macro, because macro internally here has macro symbol, which we just expanded. So what we actually do here is, you might see it up here with all of these token macro thingies. We do token macro, of course, and then we use macro symbol incbin, which is the new thing we just introduced. And of course, because all tokens have some sort of source code location information, we need to put source span in here. And these angle brackets just tell LR that we want to pass this information on to the actual parser once we match in here in our action code. And so that we can like pass the location information on to the actual syntax tree elements, that they get their location correct, which is important for error reporting. So where were we? Down here. So now we can say our macro. Of course, can't spell out macro because that's a Rust keyword. There's no way to use the R hash syntax, by the way, before you comment. It doesn't work. It doesn't compile because I think like LALR-pop's own parser of this file format just crashes on it. I don't know. I should probably report that. It's a bit annoying. Anyways, I can just do incbin here. That should work. So what we want to say, okay, a macro which returns the type macro, which are 2 different things. This is a non-terminal. This is a Rust type. Don't be confused. Incbin, and following that is a string. And these things in front here, by the way, just create a binding so that I can use it in the action code. So the action code is what is behind the arrows here, and there I basically tell LALR-pop what it should do if it encounters this thing. And that basically allows you to build your syntax tree and do some further validation and so on. For example, up here, I have some validation. You see a question mark here. That's actually a fallible macro. It could actually create an error, which will then be passed on to my program, which is really nice. I mean, just this entire thing is really nice. If you want to write any sort of parser and you can make it LR1, use LALR-pop. It's a very cool package. Anyways, so basically we're not going to use any fancy statements. We're just going to return a single macro value with its value as a macro value of include. I'm making this up, by the way. This just stick with me. And of course, I don't have an auto formatter here because it's not Rust code, so I need to format myself. The file is text and is binary true. The span is so the span is the source code location, and I have a nice little utility function, source range, which basically tells it, okay, take the first span from here, like the first source code location here, and the second source code location here, and combine them into one that spans the entire thing. There's like some minimal computation you need to do there, and I just wrote a function for that. So it's the macro to the text. So that will like show up better on error messages. Actually, I have to .1 because this text thing, this string thing, string token, is actually a token that in LARPOP retains two elements. It retains both the string data, which is a U8 vector because it doesn't necessarily have to be Unicode, and it also returns its source span. So it's not just a simple simple like source span element or whatever. It's actually a tuple of two elements. So I need to do the .1. So in the generated code, I probably won't show you because it's horrible and it's like 3,000 lines, but it's actually like this text binding. This text name is actually a tuple of this vector and the source span that you just saw. Anyways, the label of this macro is none. That's just the default value. Actually, the macro's label gets filled in later. If we have an instruction in this line thing here, you can see that we set the label on the element, and that just depends on whether there actually was a label or not. So at this moment, we don't know whether there's a label yet. Yeah, so that's all. So I should probably talk a bit more about the data structures here. So macro symbol is just like the symbol for the initial parsing and lexing step. We actually discard that after the parser, or we don't have it anymore after the parser. The parser has this high-level macro value. There's a generic macro struct, which is actually contained in the AST, and that contains, apart from the macro value, which is what the macro actually does and what it is and so on, it contains the macro's location and its label, if there is any. But the macro value, that's like where the real fun stuff happens. And we have a similar structure with the instructions, by the way. And there's like a generic one that contains all the data. And then there's one that doesn't know about its location or its labels or so on. Although in the case of instructions, one is called the instruction and one is called the opcode, I think. Let me actually check that. In the middle of, yeah, so might be, instruction is very similar. You have a label, you have a source code location, you actually have some more stuff for testing, and then you have the opcode, and the opcode just contains the mnemonic and the two addressing modes. Yeah, so that's a similar structure here. Now we have all the macros in here, and as you might have seen here, I just invented a new macro value, which is the include variant. So include, which, let me check, contains a file and an is binary flag. File, which is a vec u8, and is binary, which is a bool. Now the reason that I'm doing this is binary here, by the way, is that I'm already kind of planning ahead. I don't want this, like, I want this include macro value to be generic over whether we include like source code text or whether we include binary. Might not be the best idea, but I'll just stick with it for now. As you might be able to see, for example, for table, I'm doing the exact same thing. So all the quote unquote table macros, like the byte, DW, DL, DD, DB, and so on, they all parse to the same macro, which knows how many bytes each entry takes up. And that, of course, depends on what actual macro symbol you used. But like all of the syntax and all of the internal behavior is exactly the same. I just wanted to comment what that thing looks like. Incbin file name. Or include file name. What do they call that? I think inc source. Oh no, so it's include in wasm and it's inc source in Oh, and yeah, so ASAR has a different syntax for that. Let me see. Okay, so luckily that's not something we're going to do today. But yeah, there is a difference between WASM and ASAR. I really like the WASM style, so I would like to keep it, but ASAR is like the de facto default as far as I can tell for SNES stuff, so it's also good to kind of follow that. Anyways, we now have our include thingy, and actually I'm going to use a string here and make the action code here parse that string to UTF-8 lossy. Is that a thing? Oh, right. I'm doing it here. So from UTF-8 lossy it is with a string. So that would be text.0, which again, .0 is the actual string and .1 is the source code location of the string. So the lossy string thing, of course, will like throw away all invalid code points, which is totally fine for me, because at that point you put in some really weird characters and I don't even care if the file can't be found at that point. Yeah, so of course in other places like the string macro itself, like I don't care whether it's Unicode or not, especially because we're talking about architectures that don't even really understand ASCII. They kind of do, but not really. So then they don't even understand Unicode. So it doesn't matter if it's Unicode or not. That's why I'm parsing a U8 vector instead of, so the raw byte sequence instead of an actual string, which in Rust always has to be valid Unicode. Okay, that is incbin. Now let's see in the assembler. It's down here somewhere. Let's see. So the assembler, like the mods.rs in the assembler has the code for assembling macros. And you can see here, it tells me an error because I'm not covering include. Actually, let me check whether this compiles. Cargo check. Yeah. Right, okay, so it doesn't compile yet. Oh, okay. Yeah, that's actually something that the other code up here did as well. I forgot that UTF-8 lossy actually doesn't take its argument by value. It takes its argument by reference. So cool. Now we have this error as well, which is totally expected. Let's add that to the end. I think at some point I need to factor out some of these, but at the moment it's fine. I have way longer match statements in the assembler for all the different addressing modes and stuff. That was the wrong one. Include. So give me a reference to that. Let's say if is binary. Because we're not handling the other case yet. So if not is binary, that's just going to do, because if I later add like some parser that adds is binary as false, then this should crash it and not like give some sort of do some silent wrong behavior stuff. I don't want that. So so I can, oh no, I actually need to is binary. I can't dot out those all the time. What does it tell me? Oh, right. Getting the fat arrow. Yeah, so let us first do this exact thing, and I think I need to refactor that into a function, because what this is basically doing is resolving the file name relative to the source file, which is very important because you want your assembly to always compile the same way, no matter from where you actually called the assembler itself. Especially important with like subdirectories and things including each other and so on. So that should be rather important. So I think I'll write an actual function for that. Assemble data, does that have an environment? No, it doesn't. Well, I think I'll just create a free function. So let's see. Up here with my code, we have the assemblers. Let's just create a free function here somewhere. Resolve file, which takes in a data.source code. Yeah, so should probably do that sort of resolution itself. Takes in assembled data. Oh no, I think I'll actually take in the assembly code arc. Okay, get me back. Why can't I? Oh no, I can. So the source code is arc assembly code. The only reason it's arc and not RC is that yet my error reporting library requires all things to be thread shareable, so that's why I need to use arc and not just RC. Arc stands for atomically reference counted, by the way, if you're not familiar with like all the dumb abbreviations of Rust. Like, I hate Rust abbreviations, they're just dumb. I'm much more for the Serenity way of spelling everything out. Path, I think. And the very last thing we need to do is take a file name, target file, which is a string slice, and then we can just grab that one-liner and plonk it in there and like stop unwrapping randomly. Or do we even do that? Yeah, okay, we unwrap here randomly. Parent, what is that? Yeah, that's an option. So you can just, and then directory. Okay. Okay. Wrap that in sum. I have a semicolon here, and this should just be source code.name.clone. So this can actually be a reference because I'm not cloning the whole arc, I'm just cloning one of its elements. Target file, that's what I call that. Let's see, maybe Clippy has to say something about and then. Maybe it's better if we map. I think map. Yeah. What's the function there? It's an F. Yeah, right. An FN once. So I think that's even cleaner. Okay, let actual path is resolve file for data source code and the file name. I hope that it can just, yeah, it can actually just convert that. Let's wrap it here. Actually, let's improve the error handling with like this existing BRR macro, which is like the coolest feature of spcasm, and just have it print a file not found, because this error only happens if there's no parent directory, which is extremely strange, but I guess we can just handle it. Yeah, so cat assembly error. File not found. The OS string is source file or whatever. Just briefly format that. File name is data source code dot named clone. The source is actually data source code. Clone that as well, and the location is macro span. Okay, so location, I'm sometimes using location, I'm sometimes using span, they all mean the same. Then I can question mark that. It should be an okay or else, because this function like does a bunch of cloning, so it should only run if absolutely necessary. I need to toString this, and let's see. No, we're not getting to the borrow checker yet, because what variant are we missing? Oh, it doesn't like the, oh, it can't. It can't figure out that the if guard is complete. That's interesting. Very interesting. I mean, that's fair. Like the if guard is not the oldest feature, and I think they just do totally do no checking at all on that. What is it complaining about now? Yeah, I mean, yeah, that's fair. So Clippy was telling me that this will like match all the future variants. So if I ever add a variant, I won't immediately get a compiler error like I would like to do. Would like to get. So that's super nice. Okay, let's actually write some code. Let some actual code that handles something. Let binary file is resolve file of data source code and the file. And we're going to do the exact same thing. Actually, if we're doing that for both anyways, let's just put that into the resolve file function itself, because once we're doing things twice, we're doing it once too many. So this will actually become a result of path buff and assembly error. Just source code clone. Now I don't have a span. Then I need to probably pass the span. Span. Okay. I need to macro span. And that is all I need to do in this function. I can just question mark that, and again, macro span. Yay. Now we have a path buff. And now we can probably just tell the Rust standard library to read all the binary data from that. Can I get a file from that? Open something. Open. No. Oh, right, probably because I need to actually file. I'm not super comfortable with all the Rust IO things, the standard library. Probably open. Yeah, I probably need some file options to open it as binary. Okay, so can I const that? No, what can that even do? What the flip? Yeah, I guess there's no options for binary stuff, so then I can just forgo that entirely. Instead of s read. Oh, I can just read. I can literally just call read and it will give me a vec of u8, which is exactly what I want. That's from the binary file. Yeah, and then we need to map the error. I've done something like that above, which again maps to a thing here. I'm doing something slightly different for the BRR because the wave library actually expects a file, so I'm properly opening a file and only then reading it. Or like I'm never calling the read functions myself. The file name is file.clone. And that should be correct. If I can like actually type out things. Borrow check is happy. Fun stuff. Now that we have some binary data, we can throw it into the assembly at this point. So remember, we're currently assembling stuff, so we can actually just do things like this. I have some very nice APIs that allow me to insert resolved, non-resolved data. So I think I'll just actually copy this because it's essentially the same, except maybe I would like to no, I'll actually write a utility function for that. We're writing a lot of utility functions here, but I mean, otherwise the code just explodes. So there's a bunch of helpers for appending specific sizes of data, and they all get stuff like labels and source spans and whatnot, and it does smart error reporting and whatever. The simplest one is append currently, which just takes actual byte and its label and where it is in the source code, because I can actually tell you where literally all the source code, like all the bytes in memory, which bit of source code they came from, which I think is super cool. No, actually not. Let's not inline that. Append bytes. Let's call it that. The values are a vec of u8. Then the label is an optional label, and the span, thank you Rust analyzer. And then we just take self current segment mutable and wait. Let segment is that, and then I just paste that in there, because now we can actually like don't have to duplicate this is first logic, because only the first byte of all of them needs to be labeled with a label, which is what we're doing here. Yeah, that's not encoded, that's values for value and values, data append. No, in this case we want to segment dot push. Do I want to duplicate that code, because it's always taking a new mutable reference? Okay, let's actually self append. Like, of course I'm doing it with all the other functions. They all just call into those helpers that actually push into the current binary segment. But I mean, at this point we're dealing with like probably sometimes a couple thousand bytes, so it's like always taking a new mutable reference. Though I expect, because this is inlined, or it should be inlined, is that the that will get optimized. So that's my hope, at least. That's just label.clone and span. Actually, I don't have to clone it in that case, probably. Or do I? I do. It's probably... Yeah, so I will actually take a reference at that point. Which avoids one clone. Like, cloning labels is cheap because they're all reference counted, so you're just copying a pointer. But yeah, I don't know. It's nested in 2 levels of enums, so it also contains some tags. So I think it's cheaper to take a reference in terms of what amount of memory you need to copy. Like, that's a reason why it doesn't make any sense to have a reference to a byte, because the reference of the byte is larger than the byte itself. The byte is 1 byte and the reference is 8 bytes on 64-bit machines. Okay, let's stop with the premature optimization and see what we wanted to do. We wanted to remove this code, because now we can say data append bytes encoded macro label, oops, macro span. Okay, fantastic. And then we can reuse that as append bytes, which in our case is called binary data. And let's do macro label and the macro span. Fantastic. I'm liking this very much. Okay, now let's write a test, or let's extend an existing test. So where's my tests? My tests are up here in the examples folder. It's kind of silly, but I mean, that's just how it goes. I have ASCII, Z, and those things here. Yeah, I don't know. Let's actually create a new include. Shut up, phone. Yeah, let's just put that in here. Incbin. Just have a binary file, quote unquote binary file, but I'm actually just gonna put in like A, B, C, D, E, F, or whatever, because it's still binary data, right? Everything is binary data if you think about it hard enough. But like that will allow me to easily see the data in the, yeah, see the data. Okay. That should compile. So it's cargo run what examples include spcasm and whatever random output file test. Yeah. Not super important what sort of ELF output file we're choosing right now. Yeah, fantastic. That's just binary A, B, C, D, E, F. 61, like this is hex. These are hex digits. So that is correct. Let's try with something more expensive. I don't know. Like, for example, let's go like to a known location so that it starts at a neat 16 byte boundary. And then let's incbin the, where's that? I think that's, yeah, that's source BRR. That's kind of silly actually. I think I should move those to some sort of test resource folder, so that yeah, I don't have to have it in the source code itself, which is silly. But for now, that's source BRR the wave. That is a rather large file. Let's actually look at it in some hex format. I think those zeros were bugs. So what is that? C is, oh god, 13, I think, in hex. No, it's 12. So that's 12 kilobytes, which should make our, which technically fits in the spcasm binary. Spcasm, whatever it's called. Yeah, it fits into the memory. However, it is not the proper format. You can see here. We also have some context information, like this amount of data is already enough for several BRR blocks. Many BRR blocks. Okay, so this will be large, but I think it should work. It should spam my console, but it should work. Yeah, fantastic. Didn't actually spam too hard. So is my scroll back enough? Oh, my scroll back is enough. Yeah, I increased my scroll back massively when I did some recent Serenity stuff. Cool, so back in front here we have 52494646, which should be RIFF, and then wave or size of something, and then wave FMT, which is the wave header. I mean, I can show you again. Let me just, here you can see that. That's just how you know you have a wave format. It's the riff container, then the size of the first riff block, I think, or something like that. What's that? Probably this. Oh, it seems a bit too large. Big endian. It might be this. I don't know. Anyways, then after that you have the name of the riff block or riff chunk, they call it, I think, which in this case is wave, and then FMT I think is just the wave, the first wave block, which contains back here this is a space, but back here is the wave information. So like sample rate, number of samples, sample format, bit depth, and so on, all that sort of stuff. And then down here is another chunk probably, or another header, which has metadata. And then back here somewhere, probably after data 0, I would imagine, I'm not too confident, somewhere around here, the actual binary data, the raw audio data starts. Wave is a really simple format. That's why everyone can read it, including this random library I found on crates.rs. Okay, cool. I think I'll keep both of those in there and write a quick test that just runs this file. I already have a bunch of those, so all I need to do is yank the labels test. I'll actually bench that. So I think I should just actually yank the bench test. Okay, that worked. Oops. Wanted to press O. That's include. And that should test include spcasm. Fantastic. Let's run the test. Probably have to stop it because we have the include test. It runs. Okay. Kill that. Let's actually run a benchmark of that. It should be fast. I mean, I know it's fast. All of this code is, especially with Rust optimized, it's ridiculously fast. The benchmarker will run it multiple times just to be sure that it's actually fast. But that's not a problem. Yeah, so we have, I think I can include everything except for this test binary, which, yeah, I want to discard. Yes, delete the file, please. Okay. Implement incbin. That's literally all it's gonna be, because that's what I'm doing. Would like to. I'll just commit and push, because this is my project and I do what I want. I just push to master, and now we can cross this off our list, or I could if I was logged in, but I'm not logged in Firefox. But you will see that I made a typo. I wrote inbin instead of incbin. Doesn't matter. Let's hope that those tests run as well on CI. CI just runs the non-slow tests. Okay, I'm back. The extremely long decode has just finished, so I think we should be done in just a second. I mean, I could have just run the single encode test, or the single test that I wanted to run, but I didn't. So here we are. BRR integration, and the include test, which is super slow in comparison to all the others. That's impressive. Yeah, so I mean, I think this gives you a lot of context. The extremely long encode runs for half a second. The Rust bench runs it however many times to be absolutely sure. This is an optimized build, of course. Like you can see a lot of differences between the assembly or the machine code that is actually produced. It's quite astonishing. Anyways, these are all micro benchmarks essentially. The short sample encode is just the Yoshi mount sound from Super Mario World, and that takes almost a millisecond to encode. And BR integration is doing the exact same thing, but in an actual binary file. So it's I think it's the BRR. Yeah, so it's just doing that thing, but in a file. And that adds like another millisecond of overhead of the parser and everything. Now our all opcode test is actually faster than that, which, I mean, if I show you, it is a lot of assembly code. It's assembling all the opcodes. And this only takes, at the moment, only takes 1.1 milliseconds. I think I have some numbers on the README which tell you that like all the memory can be assembled in half a second. I think it's way faster than that. But yeah, so if you see the include test, probably just some file overhead or something, it takes way longer. Although it has to run a lot less of the assembly and label infrastructure and the parser infrastructure and so on. All the actual like, computational intensive part. Yeah, so I think that's probably not something I can fix. I could do some benchmarks, but I mean, this is fast. Like, we're talking about milliseconds here. We're talking about milliseconds here to include files that are megabytes in size. I don't even remember. Wait, no. Oh, yeah, no, so it's just the Yoshi sound, which is a couple of kilobytes. Or did we say 12 kilobytes or something? Yeah, so this is 3 milliseconds for 12 kilobytes of data. That's not too bad, considering that we have like a hard upper bound of 64 kilobytes, which we need to be able to assemble in a reasonable time frame. Yeah, anyways, this was a lot of fun. I will actually resolve the to-do. Oops, I will actually resolve the to-do in a second. This one. And yeah, see you in the next video. Goodbye.